Istraživanje našeg planeta i sunčeva sustava uzbudljiva je tajanstvena i beskonačna pustolovina. Ali glad za spoznajama o dubokom svemiru donosi određene izazove, rizike i opasnosti. Proces stvaranja inovativne tehnologije podrazumijeva neizmjerno mnogo pokušaja, pogrešaka i simulacija prije nego što ta tehnologija bude spremna za primjenu u praksi. NASA je poznata po izumima novih uređaja i strojeva. Često ne postoji uređaj koji može poslužiti kao referentna točka ili model. Njihovi inženjeri i znanstvenici moraju kreativno razmišljati, te projektirati strojeve i mehanizme prilagođene negostoljubivim uvjetima koji vladaju u dubokom svemiru, uzimajući u obzir brojne nepoznanice i različite mogućnosti s kojima će se suočiti na tom putu. Posjećujemo NASA-ine centre diljem SAD-a u želji da otkrijemo kako njihovi stručnjaci kreiraju te iznimne inovacije, te kako prevladavaju izazove i zapreke povezane s postupkom razvoja nove tehnologije. Svemirski centar Goddard jedan je od najvažnijih i najstarijih NASA-inih istraživačkih centara. Iz njega su lansirani deseci satelita, svemirski teleskop Hubble. Odatle su krenule još mnoge druge misije. Ovdje ćemo naći najveću koncentraciju fizičara, astronoma i inženjera na jednome mjestu. Pridružite nam se na putovanju za pamćenje iza kulisa NASA-inih laboratorija za proizvodnju inovacija.
My role here at NASA at Goddard Space Flight Center is a robot operator for several different missions that are helping to forward servicing and other activities that we can do with robots in space.
I'm the group lead for the robotic operator in the Nexus programs division at NASA Goddard Space Flight Center here.
Our job is to enable technologies for satellite servicing, to enable future science missions, and to help sustain a human's presence in space.
Od djetinjstva nadahnuti tehnologijom, NASA-ini inženjeri i znanstvenici danas predvode evoluciju čovječanstva.
I got into robotics as a child. I really loved building things, Legos and kits like that I could put things together and make them move and learn along the way. When I was in high school, it was the first time I got experience with programming. And that was a robotics competition that my teacher entered us in to have small robots made out of Legos play a game. And that was really where I discovered that you could sort of actually take a hobby and make a job out of this.
So I started at NASA actually as a college undergraduate when I was in Cleveland, Ohio, worked at NASA back as an undergrad. I then spent some time as I was in college interning at different NASA centers. And I finally came here to Goddard once I graduated from college. Then went to graduate school just down the street here at the University of Maryland, was involved with NASA, and then became a NASA employee about 14 years ago, and more recently joined the government as a government employee.
I started out actually as a professional musician briefly, in 3, 2, 1. That went on for a couple years, and while I was doing that the whole time, I was playing like with these large, gas-powered model helicopters, pre-drone days. So this was kind of a weird thing at the time. We can do that thing where the robot endpoint is stationary, and yet the arm is changing configurations. And I started adding little things to have video on them and have them be like semi-autonomous and provide telemetry, and I was really into this thing as a nerdy hobby. I enrolled at the University of Maryland in College Park, and after 4 years, got my degree in aerospace engineering. I stumbled across a small little robotics lab here at Goddard in around 2007, and it was kind of affiliated with people that were doing the Hubble servicing mission, which is a really amazing project and group of people at the time. I was able to get hired by that group, and I've sort of been with that team ever since.
Uz tako slojevite zahtjeve i more mogućnosti, osmišljavanje nove tehnologije za svemirska putovanja pravi pothvat.
This is the robot that we use for testing for RRM. It's one of the largest robots that we have in our facility. We use industrial robots for a lot of our testing because they're work just as well. They're easier to get, easier to maintain, and more cost effective than systems that can actually work in space. The robots that work in space are very expensive. They have to be very lightweight because every pound matters when you're launching things into space. So These industrial robots do a great job helping us out when we're testing how to use the tools. This is an early model of one of the end effectors that's actually on the robot and on the International Space Station that we use for RRM. The company that made that robot allowed us to have this model so that we could test our tools with the same hardware, the same functionality that it's going to have when you're actually in space. So we have a camera on the front so that we can see what we're doing, lights to help illuminate what we're looking at, and then the end here is what grabs onto the back of our tools, and there's a socket in the middle that actually allows us to actuate the functions on it.
Our division's involved with a few projects. You heard about a few of them. One is the On-Orbit Servicing Assembly Manufacturing Mission, OSAM-1. That's going up to demonstrate servicing of Landsat 7. Also going to demonstrate assembly and manufacturing as well on that mission. We're also involved with the Mars Sample Return Mission, which is going to be part of a module that's going to have a robot arm inside it that's going to help once the sample comes up from the Martian surface. It's going to help install it into the Earth return capsule and help assemble that capsule so it can bring the samples back down to Earth. We also take the technology developed in the division and mature them and license them out to industry to be able to transfer them to various companies around the world that want to use these, as well as other government agencies. Our partners across the United States government want to use the technologies. We mature those. A couple examples, we have a fill and drain valve, which is a way to make satellites a little more easy in the future to be serviced rather than the more traditional fill and drain valve. We're also looking at putting little fiducials, little stickers on satellites that make them a little bit easier in the future to be rendezvoused with. So we develop those technologies that industry will need to make satellite servicing possible in the future.
Over a couple of different projects, RRM, which is the Robotic Refueling Mission, where we did a demonstration on space station. The team grew, and then we did a second RM demonstration on the space station, and the team grew from that. And then we did a third one, and between the second and third one, we started ramping up to do an actual flight mission where, we would supply the robot and the spacecraft and all the tools and everything, and basically go and capture a satellite that's a friendly satellite, Landsat 7 in this case, to do a servicing operation on it. I'm standing in front of a full-size mock-up of the Landsat 7 satellite that's currently on orbit. It was launched in 1999. It's getting close to the end of its life, and we're basically hoping to go up there and grab it with our satellite and to put more propellant in it so it'll last a few more years as a demonstration mission. Underneath the Landsat 7 mock-up is a mock-up of our payload deck that will be on the end of our satellite. It doesn't have it now. There will be two robot arms, 7 degree of freedom robot arms on the end of that. Several tools and adapters the robot can use to basically break into the plumbing of Landsat 7 and put more propellant inside of it.
Robotski uređaji koji funkcioniraju pod čovjekovim nadzorom ili samostalno omogućuju NASA da uspješno odradi misije na svakom terenu.
So these are two of the examples of our tools from RRM. They all pretty much have the same kind of overall design that helps us be able to easily use them and see what we're doing as we're doing the tasks. So all of them have two cameras that are set 90 degrees apart so that you can keep track of where the tooltip is in your view, and you can align in all 3 dimensions in space with the interface that you're working with. They also all have a place for the robot to be able to grab onto them and to interface with to be able to operate the tool, an electronics port to be able to get the video or any telemetry that the tool is sending back. And then, of course, they all have the actual part of the tool that has, each one of them has its own different function. In this case, this tool is designed to be able to pick up different adapters to do different tasks. We realized it was not going to be space efficient at all if you had a complete tool for every single little function that you needed to do. So this is what we call the multifunction tool because it allows us to do many different things with one setup.
We're involved from the very early concepts. We'll do architecture studies. In fact, we've been doing that the last couple of years where we'll look at what missions are enabled by servicing, really to help us determine what technologies are needed. Whether it's building a large telescope, whether it's assembling a return capsule to come back to bring samples, whether it's maintaining a crew capsule or a crew space station around the orbit of Mars. That really helps us define what sort of technologies we need to develop. So we start with that. Once we develop the technologies we need to go and mature, we'll then do proof of concept. Could involve simple prototypes we design on computer systems. It could involve building prototypes. It could involve building those prototypes into actual pieces of hardware, putting them on the robots you saw in the various tours today, all the way up to launching things on the space station, demonstrating them to see how they will work in space, and then making the technologies part of future missions.
Nije lako razviti uređaje kojima treba upravljati s udaljenosti od mnogo tisuća kilometara. Sve treba temeljito istražiti i testirati kako bi se izgledi za neuspjeh sveli na minimum.
This is a mock-up of the Landsat 7 fill and drain valve site. We basically have a little box here that's made out of multiple layers of multi-layered insulation blanketing. Many layers of that overlapping in the corners, and it can be really thick. It's got a lot of Kapton tape on there. And basically we have to use a tool to go around the edge of this thing. It looks like almost like a Dremel cutter, and cut around the edge. Spent a lot of time experimenting, figuring the best way to do that cut so that we don't generate debris. The technique basically allows us to cut it so that we get a nice smooth cut, and we get a nice hat that'll fold open and then expose the refueling valves that are underneath. So once we've got this open, we've got 3 refueling valves. You can see you've got these big caps. They're on top. There's a secondary cap that's under this, and then there's a valve that you would have to rotate in order to actually pass propellant through. On top of that, this outer cap is wired to its neighboring caps with steel lock wire, and the cap underneath this one is also possibly lock wired to itself. It's not clear from the documentation that we have. We have to pin this back. We have a tool called the MLI restraint adapter. In surgery, they have tools to kind of like pry the workspace open so that you can see what you're doing. This is a similar kind of tool. It's designed to be installed permanently on Landsat 7, and it holds this big flap of MLI blanket open so that we can do our work inside the valve.
Some of the controls we use to control the robots in space, the ones that are near space station on OSAM-1 that are in Earth orbit, involve either keyboard commands where you can command a robot to unstow or command a robot to move to a certain position where you know a tool is that it needs to pick up to do the next task. Also involves things like joysticks. Just like you play video games, you can use a joystick to move the end of the robot, whether you move it up, down, left, right, pitching it, rolling it, yawing like you fly an airplane. You can also do things where you can display where the robot needs to go and kind of sketch a path on the computer display and tell it to follow this path, but you're doing that planning on the ground. There's also more advanced algorithms we've run where you can have the robot avoid those things on orbit, where you can tell it where it needs to go and it knows what's in its way. You give it certain things to consider. Make sure you stay in a straight line. Make sure you keep your endpoint pointed a certain way, and it can plan that trajectory as it goes along. So those are some of the ways we control robots. We've experimented with things like AR and VR, augmented and virtual reality. Those things get a little trickier because you need a very good model of what the robot's interacting with, because you need to know how to make the robot move and do different things. And so those things are a little more, I think, for the planning phases to kind of know in 3D where the robot's going to go, and it'll help you develop a better path for it to get to where it needs to go. Or we found it very useful to do an engineering analysis on the ground. We get a lot of data down from the robot. Every joint on the robot sends down lots of data. The robot itself sending data on how it's processing the imagery it's looking at, what it's doing, and that's a lot for the human to process just looking at a flat kind of display. By doing things like AR and VR, you can immerse yourself in the data, and it's a much easier way sometimes to determine what the robot's done and how to tell it to do the next step. And that's one thing we're starting to look at, of how to marry the AR, VR technology into some of the engineering analysis and planning for future robot missions.
Uređaj za proširenu stvarnost pomoći će inženjerima da još bolje rade i dublje se užive u istraživanje s velike udaljenosti.
Now we have access to the metal lock wires. We have another tool that we'll use, wire cutter adapter, and this goes on top of a tool that's held by the end of the robot like this, which is sort of like our socket wrench. It can hold a lot of different adapters on the end of it. It's got drives in the back that the robot can actuate. And we get in there with this wire cutter adapter, and you have to come at kind of funny angles depending on how the lock wire is, because a lot of things are documented really well in a spacecraft. If you have a big piece of metal, you know exactly how that was machined. Things like lock wire and soft goods, you just don't know. Once we've got the metal lock wire cut, we'll go in and remove the first outer cap. It's called a tertiary cap. It's basically just like a big metal protective cap so hydrazine doesn't leak out. And I'll note that we never put the caps back on. We only take them off. Taking them off is hard, but putting them back on with a robot is virtually impossible. It's hard for me to even do by hand to just put it back on. Now that we've got this off, we're down to our AN cap, Army Navy cap, which is secondary protection. It may have also lock wire on it. If we need to, we'll grab our cutting tool again and cut that lock wire. When we're done with that, we'll get another adapter, the AN cap adapter, and we'll remove this cap. Along with that's a little crushable conical seal that we have to scrape off and take with us because we don't want just little bits of debris floating around. And then what we're left with is a bare fill and drain valve. We basically have a tool that is almost like robotic tool version of the thing at the gas station. It's got a hose that comes out of it. This is the quick disconnect adapter. It goes on the end of our HRT hypergol refueling tool. We screw this on, and then this allows us, it's got these concentric drives to both open the valve and also to thread tightly on so that we have a liquid tight seal. Obviously, if there's any hydrazine floating around on the deck anywhere, it will eat through whatever it touches. It can sublimate quickly, but it's really nasty stuff. So you don't want it on your camera lenses from your robot or neighboring blanketing or anything else.
So some of the tasks that we do with the robots in space are things that are controlled by people on the ground, sending signals, over long distances. There's a wide range of how involved people can be with the system, either actually sending every single command, seeing video of what's coming back, and making decisions every step along the way of what you need to do next. That can also then range towards, you get signals not as often, especially if you're working with spacecraft, let's say, that are on Mars. So the signal takes a lot longer to get back to Earth, and you'll have a lot less interaction with it, that you may observe what's going on and getting data back, but the software needs to be able to make decisions and go on to the next step on its own. And then in some cases, you really don't have the person in the loop at all, and that you will just kind of say go, and the software has been created to get camera views and everything that you need, and to determine for itself everything that it needs to do.
And then once we've got the valve open, we're at a place where we can basically pass propellant through the interface. So we've got, in the inside of our servicing spacecraft, we've got a whole system that is for transferring propellant from us to them. We hope to transfer up to 40 kilograms of hydrazine to Landsat, and that could give them 5 to 10 more years of useful usage. Quick disconnect, we leave it behind. Since we've removed all the caps, it acts as like a closeout cap. And then we have a final adapter. Since this guy's peeled back like this, we have to, and we've compromised the thermal solution at this point, which is what the blanketing is for, to keep the spacecraft at the right temperature. And obviously things like refueling valves, you want to have them at the right temperature. We put our own kind of box-shaped blanket closeout back on top of this that rigidly mounts to that first tool that I showed. We can move on to re-grasping the satellite with the gripper tool, releasing it from the client berthing system, and releasing the satellite and sending it on its way.
Svemirski centar Goddard otvoren je u svibnju 1959. kao prvi NASA-in centar za svemirske letove. Danas je jedan od 10 glavnih NASA-inih centara za terenska istraživanja. Okuplja najveću zajednicu pionirskih istraživača svemira, znanstvenika i inženjera u Sjedinjenim Državama. Oni predano proučavaju Zemlju, Sunčev sustav i svemir, promatrajući ih iz Zemljine orbite. Iza Goddardovih stručnjaka, deseci su uspješno izvedenih revolucionarnih misija. Među njima se posebno ističe svemirski teleskop Hubble. Daleko od Zemljine atmosfere koja bi iskrivila sliku, Hubble ima otvoren pogled na planete, zvijezde i galaktike. Neke su udaljene više od 13,4 milijarde svjetlosnih godina. NASA je počela niz misija radi servisiranja i zamjene dijelova, tako da Hubble može i dalje uspješno izvoditi svoje operacije. Dobro je poznati svemirski teleskop James Webb, prilagođen za snimanje infracrvenog zračenja, projektiran za proučavanje najstarijih galaktika i zvijezda. Nakon gradnje i razdoblja testiranja, uskoro je predviđeno i lansiranje ovog teleskopa. Svemirski centar Goddard ističe se po izvrsnosti i okuplja niz vrhunskih stručnjaka s različitih područja znanosti, koji s mnogo strasti pristupaju svom poslu.
It'll depend on the task as to whether you can have something that's completely autonomous or not. For some of the things that we're doing for some of our missions are things that have never been done before, and you're not entirely sure what to expect is going to happen in space. So you want to keep a close eye as you're understanding what's going on for this first time and be able to give input and change things along the way. That's really a lot of what we learn with RRM. These are tasks that we hadn't done before, really no one else had tried doing before with robots, and so it was a really great learning experience along the way of, just how do we do these things, how do we adjust our designs going forward so that we can be better at it in the future.
No satellite that's launched now really has anything to accommodate refueling or repair or anything like that. They're designed and closed out on the ground so that, if everything goes well, they should never be opened up back again. They don't generally have any kind of structural things on the outside of the satellite that you can grab onto. They tape up all the areas around the refueling valves. They lock it out with a bunch of lock wire, metal lock wire. So you have to do a bunch of things to A, capture the satellite, and B, open it up so that you can do something with it. It's a challenging mission.
So a lot of it when we're dealing with something that we're teleoperating from the ground that's in space, you have a setup that will include the video of what's going on. We always, as many camera views as you can possibly get of the task really helps with being able to make decisions, especially if things aren't going exactly to plan. We have telemetry, so we watch the forces when we're touching something or unscrewing something. We know what to expect the forces should be, and so that's another cue if something's not going quite right, if we're seeing data that we don't quite expect. We get telemetry about the position of the robot, where it is as we're doing the tasks, and so all of these things are the things that we're keeping track of and monitoring. That's what we use the facility here is to test out in the first place, what should all of these things look like as we're doing the task? What should we expect? And so that's our comparison for when we're actually doing the tasks in space.
We're basically going to go up there, and we've got some tools that look like the Marmon ring, which is this big ring on the back of most satellites. That's a structural element you can grab onto. And our robot is going to look at the satellite, try to figure out where the ring is autonomously, and then grab onto that ring. It's a very fast operation, so we have to basically plan out everything in advance, all the contingencies that we can think of in advance. If something goes wrong, we don't want to bump into it and send it into a tumble. We don't want to miss because there's a finite number of tries that we get. We basically have to do a huge amount of work to make sure that we understand all of our hardware and how it'll interact with the spacecraft, and understand Landsat 7 as well as we can to make sure that when we are floating next to them deck to deck and they turn off their control system and we turn off our control system, that they're not going to float away by more than some amount, and that our arm will perform a certain way so that when we reach out and grab it with our vision system, that everything's going to be where we think it is. There is docking of spacecraft in space, but they have friendly things on them to accommodate that. So that's kind of where it starts to get scary. There's nothing like that on Landsat 7, obviously.
Zvuči kao futuristička ideja ili filmski scenarij, ali NASA-in tim mora projektirati uređaje koji mogu potpuno samostalno razmišljati i djelovati.
The machine I'm standing in front of is called a hexapod. What it is a motion platform. If you think of the way airline pilots are trained, they will, in some cases, sit in a cockpit that's mounted to a robot platform that has 6 legs that move in unison that simulate the motion of the cockpit. We have the same simulation on the setup behind me where we have a robot on one side that's reaching out to grab a satellite, and that satellite's bolted to the top of the motion platform. And what is underneath the thermal blanket is actually a sensor that doesn't exist on the satellite, but our simulation has that, so that when the robot reaches out to grab the satellite can sense how the robot has touched it, what sort of forces it applied. And those forces get fed to a computer program, and that computer program will simulate the motion of the satellite and then program the robot to move in that motion. And that's one way we can simulate the motions we want to do in space and how the satellite's going to move in response to the robot trying to reach out and grab it and grapple it.
There are a lot of different ways that you can do simulation. For us, when we're running simulations, we have the same software that is used to control our robots here on the ground, but with a virtual robot that you're creating in a virtual environment. So you take those CAD models that are being used for the real hardware, and you can put everything in, put the tools in that you're going to be working with, put the camera views in that you're actually going to have, and you can go through the task with obviously a lot less risk to hardware and see what everything's going to look like, see what your methodology is going to look like. The main things that you can't get out of that is what your forces are going to be, or exactly how many turns and what torques you need to be able to drive a tool. Those are things that have to wait for the real hardware. But as far as what your robot maneuvers are going to look like, what the camera views are going to look like, what kinds of cues you should be seeing along the way to know that things are going well, we can do all of that in a virtual environment before we actually get to the hardware.
This giant thing, this is the gravity offset table. Obviously, we don't have a good way to test, zero-G tasks on Earth. So we try to have different setups so that we can test certain aspects of that. This is basically like a giant slab of granite down here, and on top of it is a sled that's got an air tank on it and air bearings. It's sort of like an air hockey table running in reverse. And then on the front of it, we've got this ring segment from Landsat 7, or it's the same type as that's on Landsat 7. We take the EDU arm here, and we'll basically have a tool that is used for grabbing the Marmon ring. And we'll do lots of tests where we grab this Marmon ring in different orientations. We can understand the envelope of the gripper. We can understand the robot's performance when it's grabbing. Obviously it only can slide back and forth in X, Y, and rotate. But it gives us a good idea of how it will perform when the sled is free to move like Landsat will be.
Neumorno testiranje ključno je za uspjeh. U idealnom slučaju cijeli zadatak ili misija može se izvesti u simulaciji. To je obično najbolja metoda procjene svakog procesa.
Yeah, so the process we go through, we kind of bucket them in certain categories. One category is we have the known unknowns. We know on the ground we can't simulate what it's like in zero gravity. We know we can't simulate perfect on-orbit lighting conditions, whether it's the sun rising over the horizon and washing out a camera, whether it's the sun then setting and we get total blackness. We try our best, but those are kind of the known unknowns. As we sit around and we think about how can we best simulate those. And as you might guess, there's no one way to do that. We have simulations where we can go into rooms and shut the lights out and do really kind of close-in evaluations of what it looks like. We have bigger rooms like the one I'm standing in, where we can shut the lights out and do kind of larger scale simulations of what it's like to be in space with the different lighting conditions. But those are the things that we know we don't know, and we do our best to try to simulate those. We've done experiments on space station where we actually had a robot look at a back end of a satellite as the space station ran around the Earth. And during that hour and a half, we got really different lighting conditions. We got, the sun shining right down on the blankets that made the black and the gold look like the same color. And we got on the other side where there was no light at all, and the robot lights then gave us the color that we wanted. And so we simulate things in space, we simulate things on the ground to determine how is our simulation most like space and how is it not like space. And that's where we make perfections or do different simulations to get that sort of confidence that we're going to be okay when we do things in space. Similar to the motion platform behind me, it doesn't perfectly simulate zero gravity positions or free fall like you see around Earth. So we use things like granite tables that you saw in the video to simulate an object floating through space. We've flown robots on zero-G planes where then you truly are flying through space and the object you're reaching out to grapple is truly in free fall. And so we tie all those simulations together and figure out which ones simulate the best parts of the mission, which ones don't, and how can we combine the data sets to get the best simulation. And those are kind of the known unknowns. The ones we spend a lot of time thinking about are the unknown unknowns. What are the things we don't predict are going to happen or think are going to happen, and how can we either guarantee they're not going to happen, or if they do happen, how are we going to have a workaround, or how are we going to simulate to determine whether it's going to happen or not? So we spend a lot of time in groups with a lot of discipline engineers, a lot of views a lot of opinions determining how can we best simulate the mission, how can we best simulate the parts we don't know to determine whether we're going to find out how the things behave, or how do we mitigate it in case it does happen. Those are the unknown unknowns we try to simulate as best we can.
There's a big mix of what we're working with. Sometimes the parts that we're working on will start with COTS part hardware or commercial off-the-shelf hardware. Sometimes it is parts that are all designed and made in-house. the software that we use for control or things that is made in-house. And as I said, we work with other organizations. So we're working with the Canadian Space Agency and the robotics group at Johnson Space Center, that both of them are responsible for the robotic arm on the International Space Station. So there's a lot of collaboration along the way with them to make sure we understand their systems, they understand the tasks that we're creating. Everybody needs to be able to work together.
Uza sva istraživanja, testove i simulacije koji se mogu obaviti na Zemlji, u svemiru uvijek postoje nepoznanice koje se ne mogu predvidjeti.
So this is our mock-up for RM3, which is what's currently on the International Space Station. We use this for all of the ground testing that we do to develop the procedures that we then use in space. All of the different things that we were working with for this module involved hoses. And every time we work with hoses in space, we learn something new, which is really important for, in the future, being able to do refueling missions that will involve a hose. So each of these different things had a different type of hose. For this adapter, the hose had swivels. We were trying to minimize the amount of force that was getting into the robot from the hose itself. It ended up in a different position than we had ever expected or ever seen during ground testing, during space. So that was new and different, and we had to figure out how to solve that later on. This was a really interesting setup where the hose wasn't actually attached to the tool for the first time. We had a tool where you could add different hoses later to be able to work with different types of spacecraft. So that was another one where the hose started bending in space in ways other than we saw on the ground because of gravity. Learned something new. Luckily, it didn't negatively impact anything. The third thing here for the adapter has a very stiff hose and no swivels. So we're really anxious to be able to do testing with that and see what other data we can gain about how this design would affect the robot. This was the first mock-up, our first module for RM, that we actually had cameras built in instead of just relying on the cameras from the space station. So that allowed us to test the camera technology that we're also going to need for our future missions.
Many corner cases on capturing the satellite and performing the servicing where we try to think of all the things that could go wrong. And certainly there are things that maybe we haven't thought of, but we do spend a lot of time trying to figure it out. What could go wrong? And if it does go wrong, how can we gracefully handle it? We do that by testing in the lab. We have a lab filled with several industrial robots, similar to this one next to me here. It's a large Motoman 7 degree of freedom, 50 kilogram robot. We have an EDU robot, and we do lots of work in simulation as well. We test, and where we can't test things, because you can't test everything in 1G, and have it perform the same way that it might perform in 0G. So for things where we can't test in 1G, or it's not a good idea to test in 1G, we have simulations. We spend a lot of time building up the simulations using real hardware to verify that the simulation is acting in a realistic way. So either we're spending a lot of time testing on hardware, or we're spending a lot of time on hardware making the simulations really, really good.
So in order to develop new technologies, it really depends on what sort of technology we're talking about. If you're looking at a robot system, which is pretty complex with software, electronics, and hardware coming together, that could take 5 to 10 years. If you're looking at a new mechanism or a new latch or, say, a new fill and drain valve that will enable satellites to be serviced in the future, that could be in the order of a few years. One of the biggest inputs in that is depending on how mature the technologies you're already advancing. If it's something brand new or that's never been done before, that obviously takes a little bit longer to come up with initial concepts and to try out a few options and then develop the final product. If you're taking something that's already flown and making it a little bit better or applying it to different application, those can be done a little bit quicker, usually in the 3 to 4 year time frame, obviously depending on budgets and the team you have to put those together and make them applicable for space.
Čak i uz brzu izradu prototipa, simulacije i izdašan proračun, može proći nekoliko godina prije nego što se nova tehnologija može primijeniti u svemiru.
The flight arm design has 7 joints on it. It's a 7 degree of freedom robot arm. And this robot has an extra joint that basically allows us to do kind of like what your arm can do. When you grab something, you can swing your elbow around. You can put the end of the arm where you want it, and then have the rest of the arm in lots of different configurations, which is helpful if you're working in close quarters like we are when we're doing the servicing tasks. Also on the end of this arm, you can see there's a lot of stuff happening at the end. We have a tool drive called the ATDS, the Advanced Tool Drive System, and it basically has multiple rotary drives on it and a drive that can stick out, actuate something. and it can also couple and uncouple tools. They're not installed right now, but there are 2 tool cameras that would be on the end of the arm here. And that would be so the robot operators can see what they're doing. So you get up to the work site and you kind of have this like tool's eye view of the work that you're doing. And the little cameras can pitch down and up, and they can extend and retract depending on the tool that you're using. So you have these 2 nice kind of like right angle views of the work site. And it makes aligning to the work site, which for a satellite that was never meant to be serviced, doesn't have any friendly features on it. You need to have some way to be able to do that.
One of the new projects that I'm working on is involving using a robotic arm on a spacecraft that is in orbit of Mars, and being able to prep a sample that we're going to be bringing back from Mars using the robot arm to do that. So that's definitely a much longer distance, a different way of operating because of how far away we are, but still taking the lessons that we're learning from everything that we do both on the ground with the International Space Station, and being able to apply that going forward for new missions.
A couple of things I like most about the job. One is the fabulous team I get to work with. A lot of smart people from lots of disciplines, not just science and engineering, but our outreach team, the legal team we work with, the financial team. I'm learning things from those team members every day. And I think the most joy we all get is solving new problems every day, right? One of the things NASA, I think, prides ourselves on is we solve the hard problems, things that have never been done before. And I think, every day, just about you're coming in with a new problem you're trying to solve, whether it's a new mission, how do I assemble a large telescope into space, or a project you've been working on for the last 10 years and you come in and want to simulate something that we just discovered yesterday we might have to be concerned about. Whether it's a different lighting condition or a different way the satellite's going to move or a different robot algorithm we need to develop or a new piece of technology we need to mature. Those are the exciting parts of the job, because really every day is something new, a new challenge we get to go off and solve as a team, which is really, really exciting.
You're constantly having to try and imagine how things might be different when you do the actual task, and is that going to cause problems? Do you need to alter your methods just in case, so try and keep yourself from getting into trouble. We still get surprised sometimes, and then that's actually some of the most fun when you have, a really smart team of people here and at Johnson Space Center that we're all working together to figure out what do we do on very short notice for something that we hadn't planned was going to happen. And it's really exciting to do that problem solving, in real time, and then actually test it out and see what happens in space.
Mnogim NASA-inim robotima mora upravljati čovjek. To se može raditi na mnogo načina.
Mainly what we use, we have a large robotics lab where we have developed our own software. We've worked with industrial robot manufacturers to basically allow us to kind of get into the robot control at the very lowest level. So we have high-speed controllers for the robot. That's not a normal thing. Most of the time when you have an industrial robot, on an assembly line in Detroit or whatever, the robot goes back and forth and back and forth. Our robot, can move around its workspace. We can drive it with joysticks. It's got a wrist-mounted force sensor on the end of it. It can behave differently depending on what it's detecting from its wrist-mounted force sensor. So the operator can tell it to do something, and then the robot can say, hey, I feel some force and some moment in these axes, and then basically respond to not overload the robot or whatever it's touching.
So a few things that are very exciting about the job is, one, some of the technology you're developing will allow us to build the structures we need in space to eventually find life on other planets and around other solar systems, which is very exciting. Thinking about how we evolved, where we came from, where we're headed, to be a part of that, even a small part, to enable that future is really exciting. The other part we're really excited about is we're actually bringing samples back from Mars. And so to actually get those samples back on Earth, to be able to look at those, was something NASA's been talking about, the world's been talking about for the last couple decades. Be part of that is really exciting, to actually get those samples back here on Earth, to use the greatest technology that we can't send to the surface of Mars, to be able to look at those samples and determine if there's life on Mars, which some think that's where life evolved from here on Earth, is really exciting. So I think to really think about yourselves in the global scheme of how life was created, to be part of that is very, very exciting and very motivational to come in and do that sort of work every day, to enable the technologies to allow the world to go out and explore and find those sorts of future science discoveries.
There are lots of different places that we want to go in the universe that we aren't quite ready to be able to send people yet. Or when we are ready to send people, they're going to need help along the way to be able to keep themselves safe, keep their spacecraft safe. So these are things that we're learning to do. We also have many, many different satellites that are in orbit right now that don't ever have any intention of sending people to them. And so instead we can send these unmanned spacecraft with robots to be able to fix them, keep them running for longer, as I said, repair things if they break, and so, be able to fulfill their missions for longer periods of time.
NASA-ini stručnjaci iz centra Goddard puni su entuzijazma, vrlo odlučni i predani. Strastveno pristupaju radu na svakoj misiji, čime dodatno obogaćuju i jačaju cijeli proces.
My hope is, we've done these demonstrations on the ISS for the Robotic Refueling Mission, and now we're doing a mission where we're doing it on a live satellite. And I think once people start to see that, hey, this was the worst case, basically, the hardest case. You're getting into a satellite that was never meant to be serviced. If we spend a little bit of extra money and put on, one of these standard valves or standard targets, then basically you can, refuel or repair most any satellite. It's a hard thing to convince the community of that, but a successful demonstration will go a long way.
Sometimes when we talk about the ideas, it even sounds impossible to us, but then that's our job to go make it happen. So that's one of the really exciting things, is just things that sometimes we can't even believe that we're doing are the things that we're actually getting done.
For the future, I see some new robotic technologies being utilized. Certainly as our tasks become more routine in space, whether it's satellite servicing, building habitats, building large telescopes, those systems could be more autonomous, whereas today they're more controlled from the ground because this is the first time we've done this sort of thing. So as we go further and further out in the solar system, we get farther away from Earth. Requires us to put more autonomy on board, to have the systems think for themselves, react to situations. It doesn't require sending signals back to Earth for someone on the ground to look at what happened and then send new commands up. Also, I think as we have robots working side by side with humans, whether it's exploring planetary surfaces, whether it's working outside of spacecraft, that's going to require a different set of robot autonomy to allow the robots to work side by side with the humans. And I think those are two areas I'm excited about for the future to enable more exploration of the solar system.
Pred nama je uzbudljiv put u nepoznato. Konstruiranje futurističkih alata koji omogućuju sigurnost i uspjeh na tom putu jedan je od NASA-inih zaštitnih znakova. Roboti i umjetna inteligencija postali su temelj naše evolucije u svemiru. Zahvaljujući njima, ljudi mogu sigurno obavljati teške zadatke na negostoljubivom, neistraženom terenu, što NASA ubraja u svoje prioritete. Umjetna inteligencija i samoodrživi sustavi sigurno će imati važnu ulogu u našoj budućnosti. Ali za sad ljudi i dalje moraju upravljati uređajima i nadzirati njihov rad da bi osigurali uspjeh procesa. U sljedećim nastavcima otkrićemo još iznimnih inovacija u NASA-inim centrima visoke tehnologije.